Hello and welcome to QED Lecture 5 Part 10 on confidence intervals. So a hypothesis test answers one specific question, and normally that is a question that the author has in their mind. Confidence intervals empower the reader by letting them answer their own questions. For example, suppose you have this information about a sample of households from rural areas, sample of households from urban areas. Can the reader say to themselves and answer these questions themselves? Is there a difference in mean incomes between rural and urban? Is the rural income below $3.50? Just pause the video a second. Can the reader answer that themselves? And the answer is no, they can't, because this is just a sample of households from each area. Could be in the whole population that there isn't a difference between rural and urban, or even it's reversed, could be. And it could be in the whole population that the rural income is not below $3.50. So you can't answer either of these questions. However, if you also give the reader this information, based on a calculation, that 95% confidence intervals in each area, based on the samples, were this for rural areas, this for urban areas, then this is saying that in the population we don't know exactly what the rural mean is, but we think it's somewhere between here and here for urban areas. Then you can conclude that yes, there is a difference in mean between rural and urban, because these do not overlap. This number is less. This is less than this, but you can't say there's strong support for the idea that rural incomes are below $3.50, because $3.50 is within this area. So the reader for themselves, just reading this, can answer both these questions that occur to them. So confidence intervals gives the reader a lot more power to interpret the data and understand what you're trying to say. How you actually calculate them, well, they're closely related to t-tests. For example, suppose you had 9 heads of household in a sample. These are the ages of heads of household. You can use that to, for example, answer this question. Could the mean age in the population be 43? So to answer that, you do a single sample t-test. So the p-value comes out as 0.3883. I've just done it in Excel here. Here's the sample. Here's all the calculations you've seen before. There's the p-value using the calculations you've done before. This just shows you diagrammatically what the probability comes out as. So here, definitely can't reject H0. So you would not reject 43. Fine, so much for the t-test. A confidence interval is a bit like doing every possible t-test all at once and see which null hypothesis you'd reject, which ones you'd accept. The way you do it, really, there's a formula I'll show you in a minute, but if you were doing it by trial and error, you do it like this. If I change that from 43 to 40 and recalculate it, I find out that, okay, I still would not reject, but it's closer. Because previously 43 was really close. Now 40 is a long way from what I actually found. So my sample is saying to me, hey, it's not very likely to be 40, because if it's really 40 in the population, there's only this chance that I can get a number as far away as that. But it's okay, it's more than 50, it's more than 5%, so I won't reject it, but it's close. If I go further to 39, okay, could it be 39? Then no, that's too unlikely. If it's really 39, the chance of getting 45 as far away as that is 2.5%. So at 95% confidence, I would reject that. So if I'm working at 95% confidence level, I would not reject 43 or 40, but I would reject 39. So there must be somewhere in between 40 and 39 where rejects turns into don't reject. And if I went back to Excel, see here's 43. Please just fast forward through this if you don't want to see all this, but 43 I can't reject, 40 I can't quite reject, 39 I can. So if I went for 39.5, okay, that's still, I still would reject that. So 39.8, I'd still reject that. 39.9, I'd still just reject that. 39.95, oh, I wouldn't quite reject that. Oops, that didn't need to go that way. I would reject that. So that's like a 39.94 roughly. Yeah, so it's around about 39.95 is just that borderline. So by trial and error, we can find that, yeah, okay, this is close. 39.945 is exactly why I could neither reject nor accept on that borderline bet. Anything below that, I'm going to reject. So that means that I can kind of rule out, just from looking at my data, I can not only reject particular values, I can say that I would reject anything below that. So that gives you that range. Anything above 39 is okay. Anything below that, this particular number is not okay. Except that obviously there's an upper limit as well, because I can reject that. It's not going to be 100 or 60. I just repeat this same process and see what's the maximum I'd be okay with. Yeah, so that's what we found so far. There must be a boundary edge. We found that, it's 39 point something. You can also find an upper boundary edge in the same way. So this is what we're doing at Excel. We're saying, okay, what about, so if this won't crash, what about 49? So 49 this time I found 4 below, but I wouldn't reject it. 59 presumably I'd say, yeah, definitely reject. No way I'm going to get that far below. So you have to kind of test around. I think it's near 50. You can experiment around. I won't go through the process on the screen because that's not that exciting, but by experimenting you can find that 50.054 years is exactly on that. So anything above that I'm going to reject. So what we found is that anything below that we reject, anything above that we reject. So we call that our confidence interval, that anything between those values we would not reject if we did a t-test based on a 5% confidence interval. So that's what a confidence interval is saying. It's saying, okay, we're not sure exactly where the population mean is here, but we would not reject anything between there and there if we did a t-test. So that's quite a good range of values that we can be confident it's lying in there somewhere. So calculation I'll show you in a minute, it's very easy, and in Stata it's extremely easy. Stata, you can just type in this command, for example. There's lots of commands in Stata that when you put them in, they give you the mean, and they also give you this confidence interval as well. But here's one you can actually ask for it and say, give me a confidence interval for the mean of this age. This is a variable. Here you can tell it the level, 95. You can put 99 or whatever in, but 95% gives you that. You see it's pretty much the same numbers we just got, slightly more accurate. To do it like by a formula, like this, first of all, you need to look up in your t distribution what value of t cuts off the top 2.5%, giving you 97.5% on the left. And here, it's a bit tricky to draw this, but we should try. Just get a pen. So you're looking at a distribution like this. This is a t distribution here. That's 0. That's t star. What I want to have is 2.5% here. And this way, I want to be the other 97.5. No, it's 97.5. So 97.5 is less than that, all the way down to minus infinity. 2.5 is above that. Question is, why am I looking for 2.5 when I want a 95% confidence interval? Instead I've got 97.5. However, confidence interval is you're cutting off too high and too low. So what you also want to cut off is, let's try to, this is quite a nice sign, quite a nice colour. Well, that sort of thing. I hope it's okay for people that don't distinguish colours too well. Please tell me in the comments if it's no good for you. If you took the same value you got here, t star, but negative, then because it's symmetrical, here you're going to get 2.5% as well. So between here and here, you'd have 95%. So you get 95% between positive and negative, that t star. That's why to look up the t star, you look for the 97.5%. Anyway, if you did this, you think, okay, if I was doing a t-test, when would I reject it if it goes too high? It would be like in this situation, when that t value comes out as bigger than that t star, you'd reject it. But this equation here, you can rearrange, if you remember that from your GCSE or A-level. Multiply both sides by standard error. Take the x across this side, so you've got minus mu here, minus x, and this times this positive, and then multiply the whole thing by -1, which switches around the inequality. So you arrive at this result. So mu can't be any bigger than that. That's the maximum mu can be. It's the sample mean you found plus this t star times the standard error. Then if you look at what happens if you're going to reject it when it's down here? You have to start with less than negative t star. So if you change that to less than negative t star, and then rearrange that, then you get the part that works for the bottom of the, coming to the next slide. That gives you this bit here. Mu must be bigger than this part. So mu's got to be in between x, the sample mean minus t times the standard error, and the sample mean plus t times the standard error. That's the confidence interval formula, like this. We can see that the centre of that confidence interval is the sample mean, and then it's plus or minus this width. And that's the width of the confidence interval given by this factor, the t star and the standard error. And these are the factors that affect it. So the more spread there is out there in the population, the more difference there is between one individual and the next. That's going to make the population standard deviation bigger, which means that you'll get more spread in your data. So your value of S will come out bigger. So the value of S is bigger, the value of standard error is going to be bigger. This number here is bigger, so you get a wider confidence interval. So that kind of makes intuitive sense that if there's much more noise in the population, it's hard to be accurate about where the mean is. You can't control this. The next two you can control. What confidence level you choose. The higher the confidence level, the bigger that value of t star has got to be, because you're chopping off a little bit at each end. This one you chop off 2.5% at each end. This one you chop off only 0.5% at each end, so t star's got to be bigger. So the higher the level of confidence interval you choose here, the wider the confidence interval must be. And finally, the sample size, so that when you make n bigger, it makes the t stars get slightly narrower, because the t distribution shrinks towards the normal distribution. More importantly, the standard error gets smaller, because standard error is s divided by square root of n. So you're dividing by a bigger number, so you're getting smaller standard errors, so that width decreases. Okay, so that's confidence intervals. Before we look at conclusions, let's take you off to this wonderful thing, which is almost as good as the sampling distribution demonstration. This is links to from the Blackboard site. So this is confidence intervals. So in the controls on the left here, you can simulate what's the sample size. So I've set this up for the example we've just been using. So sample size is 9. We had 9 households doing 95% confidence interval. Population mean is, we're hypothesizing, is around 43 roughly. Population standard deviation is about 6 points, about the same as the data we have. So basically, this is showing that if you took 5 samples and work out that confidence interval, then in all the cases, the true mean is captured. So I'm just assuming, just for this example, that the population mean really is 43. So in that case, that in every one of those samples, it's captured it. So that's just conceptually what was happening if you go out and sample another 9 people, do the same mathematics, the same sum we just done, work out the confidence interval, it would be between there and there. Then go and take another sample of 9 people, do the same sum, you get slightly different values, but you get the confidence interval between here and here. Next sample here and here, here and here, here and here. In every case, when you've gone out and done the confidence interval, in every case, even though you didn't know exactly where it was inside that confidence interval. If you only give people the mean of the sample, it's like just giving them that blob. And they've no idea from just that blob how close it is that the real population mean is likely to be. That's the good news. The bad news is if you do this 100 times, yeah, sometimes, like in these red cases, it goes wrong. Like here, we missed. So the true population mean wasn't inside it. So you might just get a sample where it doesn't work. I'll just do another. That's worse. 1, 2, 1. So there's 7 times. 1, 2, 3, 4, 5, 6, 7. That's quite bad. For example, this one here completely missed. And there's 4 missed there. There's the textbook case. Because in the long run, what you'd expect is that in every 100 times you do this, every 100 samples you collect of size 9, go through the thing and calculate the confidence interval, about 5 times out of 100 you're going to miss. So that's the risk with the confidence interval, that maybe your sample is one of those 5 out of 100 where you miss. If you want to overcome that a bit, you can increase the confidence level to 99%, and resample it, and that's the good thing is that you miss less often, only about once in every 100 times on average, sometimes a bit more, sometimes a bit less, but on average about once in every 100 times. But the other downside to that is you have to make it slightly wider so it's less precise. If you wanted much more precision, you can go for an 80% confidence interval. It's really narrow, but then the downside is that 20 times out of 100 you miss, so is that really worth it? Probably not. So which is why the compromise ones are around the 90–95%, when you know it's reasonably accurate and you don't miss that many times. So that's what the confidence means. It means that if you repeat this whole thing 100 times, that's how many times out of 100 you expect to capture the real population mean. Okay, finally, to conclude, the conclusion section is fairly short. I'll keep it in the same video. So the conclusions are that the logic and the terminology of all hypothesis tests is very similar. There are certain concepts and languages we use for any kind of tests. For example, there's the null and alternate hypotheses, there's rejection, there's non-rejection, there's making type 1 and type 2 errors, which you can make with any kind of test. You need to be clear about what those are. So please review that carefully from the slides, type 1, type 2 errors, and how that relates to their alpha and betas probabilities. So that first section is for any kind of test. Then we boiled it down to particular types of tests, which depend on the kind of hypotheses that you're going to try and answer and the kind of variables you have. So for testing means and differences between means, that's where a t-test is your friend. So single sample t-test or differences between means is the independent samples t-test. That's when you have a categorical variable and a scale variable. When you've got two scale variables, testing correlations is a good way to go. When you've got two categorical variables, usually nominal, testing associations with a chi-squared is the way to go. And then finally, whenever you're giving any information on scale data, when you're giving some means, please don't just give your mean. Always give the confidence interval, because it really empowers the reader. The reader knows how close to your sample mean is it likely that the population mean is. So confidence intervals really empowering. I recommend that you routinely report confidence intervals every time you give the results for scale data that you collected or that you're working with. Okay, thank you very much for watching and listening. Please, questions, feel free to get in touch, put things in the forum and so on. But I look forward to seeing you in the next class, and thanks very much.